So friends, so we are into our fifth lecture, that is last lecture of week 2 in dependability engineering, and here we will be discussing maintainability, because we have discussed reliability, availability, and now what is remaining is maintainability and safety. The safety and risk modeling we have already discussed in our introduction lecture, but just for the sake of continuity I will be discussing this. And second reason is the risk modeling or safety modeling is an independent chapter. So we will go into the detail, but for the sake of continuity, if somebody in isolation is seeing this lecture, he will see all the components of dependability. Of course, security we have not discussed and all, but again that is also coming as a special chapter. So we will be focusing more on maintainability aspect. I am Professor Prabhakar V. Vardhe, and now CEO of ERMC, Engineering Risk Assessment and Management Center in Mumbai, and I am a guest professor at Lulia Technology University, and I have worked for 35 years at Bhabha Atomic Research Center, retired as an Associate Director, Reactor Group. So let us start the lecture. So first background is like this, that this is the last lecture and we have discussed reliability, maintainability, availability in detail. We have discussed complex modeling using Markov model for availability modeling, and now we are in this lecture we will be discussing definition of maintainability will start and derivation of maintainability equation. Okay. Sometimes or to a great extent it is like, what is FT, probability density function, in failure domain. We have here maintainability function. So that kind of similarity you will be seeing when we go for this derivation. And introduction of safety modeling, it is just for the sake of continuity that we have over here. So what is the significance of maintainability? If a plant is having a very good availability factor, that means maintenance staff or maintenance component of the system, they are very effective, and the consequences of failures are reduced to the minimal level. That is how the availability factor is good. Now when we talk of risk conscious operation management, maintenance is one of the inseparable component of operation and aging management. In fact, in aging management, the extended maintenance or life extension of the plant is fully taken care by maintenance management group. So management becomes very important during operation also and during aging management also, and that is how it reflects in availability or plant life extension. Now excellence in maintenance directly reflect in the plant, reduction in plant availability, as I said, impact plant's reliability also, because frequent failure of the component they affect the plant reliability also, or plant mission also, and availability. Okay. So, but one important thing is maintainability or maintenance is very human resource intensive in terms of number of human resource or the size of the human resource, and also in terms of the training level or their expertise level. And that's how, of course, the maintenance depends on logistic, spare parts, so many equipment that are required, fixtures and all, availability of those things. But essentially the human resource is directly impact the maintainability or plant availability. And that's why in special domain, the special training schemes, they take care of maintenance staff for using special curriculums on maintenance. The maintenance technology has evolved with the industry, maturity of industry and the technology. To begin with, it was breakdown maintenance. If the part fails, the industry may or may go to shutdown state, the part is repaired and again the process is started. But then it was found very expensive, or so to just one part or a couple of parts, they take away the plant availability. So the concept of preventive maintenance came in. That means proactively do the maintenance based on the periodicity, and this was based on experience. So preventive maintenance, it worked and it is working even now also very effectively, that before the onset of failure, the parts are repaired, whatever deficiency was there, that was managed, and finally it doesn't result into the consequences. And again, if we say redundancy, diversity, they are also add to the maintainability thing, because if redundant channels are there, as we saw in the Markov model in the previous lecture, we can take one channel out for maintenance. So it was a big gain. So one channel at a time we can do maintenance, and that is a inherent provision to increase the maintainability, typical case. But then as we are evolving, technology is improving, data are available, materials are better understood, the condition based maintenance has been occupying bigger and bigger dimension. And the technology is that sensor technology, monitoring technology, they have evolved. So if I want to monitor a critical component of a critical feature of a equipment or if of a plant, I will do online monitoring. So signal, the online monitoring signal, it could be vibration, it could be temperature, it could be leakage. So through that I'll keep monitoring the condition of the equipment that we are monitoring. Like let's say bearing. For bearing, what we require is the pump is operating, but if I monitor the vibration level of the pump, if I monitor the temperature of the pump, if I monitor the oil viscosity, or if I monitor the turbidity, oil turbidity, then I know in perpetuity what is the condition of the pump. The increase in temperature will tell me that there is something wrong, and immediately the action can be taken, or it can be determined when this pump should need shutdown and corrective action. Okay, so condition monitoring was based on whatever signals are coming, instantaneous signals are coming, analyze them and work out the strategy for the maintenance or planning. But then now it is the time for predictive technology. Predictive technology means the science of material, the science of monitoring has so well advanced that we are able to predict the failure in advance or consequence, or we are able to predict even the aging or wear out that is taking place in the component. So now this predictive technology, and as a consequences of this, the prognostics and health management, it is a complete package solution. Especially for electronics, it has developed a lot, and though it has not reached all the industries, but it's a potential shows that like reliability has got one weakness, that its probability can be assessed, but the instant of failure cannot be predicted. When the component will fail, it can be today, even though reliability is very high, it will fail today, it will fail tomorrow, or it will fail after 1 year, or that cannot be said, but it is low. So, but then here in the prognostics and health management or predictive technologies, you can track the degradation. It could be vibration, it could be temperature, it could be some material properties, and then say the remaining useful life for the component is this much, so that you can management component is there in PHM. So then we can say, okay, this repair or corrective action can be taken after 1 month, or it can be it requires immediately to be done. Those things can be determined. So it's a complete solution in itself. But if you require PHM, it is what I told you about data driven technique. But there are some physics of failure model which is purely in the area of science, how a crack will initiate, how it will propagate, when it will become catastrophic. It is difficult, but then the secondary symptoms, that is temperature, pressure, vibration, all those things, they can tell us how it is evolving. So integrated techniques are used, physics of failure base as well as data driven techniques are used for prognostics and health management, especially where critical. Now these techniques are very expensive, PHM, predictive technique. So the risk assessment brings a very effective solution to prioritize the techniques actually, whether it should go preventive maintenance is okay. Some can even tolerate breakdown maintenance, and it could be economical also, because it does not have any direct consequences on the plant availability, safety or risk. And one more special domain is which is coming in reliability or risk centered maintenance, and this is evolving because now people have plant data, their performance, their behavior, performance, so that maintenance plan can be worked out. So it will not be like static plant, like a preventive maintenance. It will be the components are failing more, they are becoming unreliable, their maintenance is more. If the component is corrective action is taken and the failure causes are eliminated, then we can have a very large span for maintenance. So risk and reliability, this is one thing. So, risk, what component contributing to the risk, it cannot be. So components which are critical to safety or risk reduction, they should be given priority. And here is one example of risk monitor. Risk monitor means it is built based on the model of the plant, and then as the component goes, the plant availability goes up and down due to which component failure. So it reflects. So if I want to take out a component for maintenance, I will see if I take out that component, what is the risk level, that is increases or decreases. So I have seen for me, if I take out for 1 hour, 2 hour, 10 hour, what is the consequences, how the risk model impacts that outage of one component. Like I told you, one channel we can take it out for limited time, but if I want to take it for higher time, then plant risk increases, and then the action. But of course these are all happening through independent body or regulatory approval or administrative approval in the plant, because it has got impact. So risk monitor is becoming a sort of part and parcel of management of plant shutdown, maintenance and operational actions. Now let us understand what is maintainability. Maintainability is defined as the probability that a maintenance and operating environment will facilitate the implementation of high quality maintenance function in an efficient and effective manner, such that equipment and services are restored to operational readiness in a timely manner. It is a complete description, and it is even maintainability, we can note here, is remains in the domain of probability, because maintainability can be defined as the T is the time which require random variable for repair times. So MT, that is maintainability, as a function of time, repair time, is nothing but probability that the maintenance job will be completed in before the time T. T is a random variable and time T is the designated time. So MT, and given the condition. So, it is similar to something like reliability equation that we have here, maintainability equation also has got, but here the difference is instead of failure, it is the repair rate that comes into the picture. Now, P is a probability and T is a random variable, and that is what we can make out from here, and this is the target time for repair. The repair overall time of the equipment has been observed to be random. To a reason it cannot be attributed sometimes. Even if we do everything perfect, so it is better to consider it as a random variable and solve all our or address all our issues. And it provides a mathematical framework. That is the biggest advantage of so we can see here, if probability density function maintenance function is GT, like we had in reliability failure probability density function. So, it was FT. On similar line it is GT here. So, maintainability is equal to 0 to T GT dt. Integration over time, you will get a mean time to. So, the above equation is what we have it is a probability density function similar to earlier in reliability it was F exponential lambda exponential minus lambda t. So, it is GT is equal to, it is a repair rate comes into the picture, mu is nothing but repair rate. Okay. So, maintainability is 0 to T repair rate exponential minus, and then finally you get like reliability 1 minus exponential of this term. Okay. So, we got the equation for maintainability. Now, if I to get like mean time to failure, if I want to derive equation for mean time to repair, then I have to go, you know that again analogous to our mean time to failure, we have mean time to repair 0 to infinity T GT dt. Now, integrate it, you get this in T mu exponential minus mu T, and so GT value, put the value of GT mu exponential minus T, T remains same dt, and solve the equation, and we get the equation for mean time to repair. So, we got a very good model for maintainability here, and we got mean time to repair equation. That means, mean time to repair is inverse of repair rate, like mean time to failure was inverse of lambda. So, it is easier to grasp this concept, and we have here is part B was risk assessment. Probably I have repeated deliberately the same slide just for the continuity. So, we have discussed maintainability, maybe some example can be seen in the book and can be solved, so that we have more feeling about how maintainability mathematics works. So, we have the definition of probabilistic risk assessment and over here, and then for risk based engineering or RCOM, we have adopted this definition as a comprehensive, systematic and structured analytical approach to postulate the potential accident scenario by considering numerical data on the likelihood and consequences for arriving at a quantitative estimate of risk for complex engineering system. Okay. So, we have this procedural steps in lecture week 1 I have explained systematically. So, no need to go through it. Then we have fault tree for system analysis. We are heading towards risk modeling actually. So, this is the fault tree that was drawn, and then it was a reduced fault tree, and with that we have generated minimal cut sets. Here common cause failure, diesel generator, diesel 1, 2, these are the combination which will lead to the top event. Okay. And then we have this accident sequence modeling, and through using the event tree, and here we have the various accident sequences. Only first is a safe state, threat state, and threat means deviation from safe state, they are not going to unsafe direction. CD, when I indicate here, this is unsafe direction, unsafe state. So, various 13th accident sequences are made. When you add all this, these are called loss of upside power rate. If you add up all these things, it will give us contribution of loss of upside power to the core damage. And if I want to do a percentage contribution, okay, so we saw that quantification. So in fault tree, we quantified failure probability for various situations should have come before, estimated this class 3 on demand failure probability, and here we ended up and again, so accident sequences adding together will give a core damage frequency. So that was a statement of risk. Now we got some special area. Probably in 2 instances in this week, I was able to highlight the importance of common cause failure. Okay. Human reliability, it is the central chapter in risk conscious operation management after risk estimation, because human impact right from conceptual stage to design stage to operation stage to maintenance and to aging management stage, every humans are involved. So they have to be factored in, and the uncertainty in human reliability estimate has to be reduced. It is one of the major problem the risk industry has been struggling to reduce the uncertainty, and the risk conscious operation management approach says for reducing the uncertainty, you should have a human model. You should have a human model, and you should have a system for assessing the root cause of human error or human mistakes or lapses or whatever. So, and then uncertainty analysis. We use a probabilistic notion. We have the upper bound, lower bound calculation for uncertainty analysis, how it is to be interpreted, how sensitivity analysis has to be. These are the special topics in dependability analysis, which intuitively does not form part of the dependability equation. But for complex engineering system, they require attention. And role of intelligence or machine learning algorithm. If I have to reduce human error, I have to have an operator advisory aid. Just assessing the human error is not sufficient. So what are the aids you should have? So intelligent aid that will be available to the operator not only during normal operation but also in emergency condition, so that his stresses goes down when he sees and the best part of this approach is the due to emergency situation, the computer does not get affected, but human get affected significantly, because the stresses on cognitive level they adversely affect the performing capability of human, but not that does not apply to the computer. So computer based intelligent algorithm, they can go a long way in reducing the risk and increasing the safety. So maintenance background, we saw operation perspective, their integral part, evaluation of maintenance strategy, derivation of equation for maintainability, mean time to repair, and risk modeling. Just for the sake of completeness, we have discussed in this lecture. So if I have to conclude or give final remark, so dependability aspects are fundamental to operations management, because operation depend on so many factors and they have to be evaluated and updated. The traditional approach is structured around RAMs, which is not complete according to the new paradigms that are available. So new elements like security risk need attention. It has become very important. So if it is not part of RAM, so what we have to say, S term should occupy the random failure component as well as security risk, deliberate attempts, random failure and security related issue. If safety is an overriding factor, the question is why not make integrated dependability metrics centered around risk by considering safety risk, security risk, loss of reliability risk. Because when we see the plant perspective, reliability is very important for continuous operation, but loss of reliability, any interruption outside to the stakeholder, it brings in the safety issues. Power supply available to a plant, if suppose there is a power plant producing electric power, and if it fails, it doesn't supply power to the hospital. Patient's treatment is adversely affected. So there are risk issue to the in public domain. Maintenance risk. Any error in maintenance, if it remains as a latent fault, like calibration error and all, it will precipitate when systems, safety systems are demanded. So maintenance risk can be considered an availability risk. The data will show that plant availability is adversely affected sometimes by accidents, that is risk factor, or sometimes recovering the plant. Sometimes after the accident the plant may go permanently shut down. So availability and risk, they are also connected. So why not make a risk matrix? And this, what I am putting on the slide, is a research topic, because my student, they should, apart from what has been taught at academic level, they should be prepared to go to the R&D level also, or so that they can give new solutions. So the last bullet, that is why not make integrated reviews. And I think this matrix, which is centered around risk, ensures effective approach to performance also. There are some references which you can see here for writing, for drafting this presentation, preparing the, I use these references, and they are from my book actually. So if somebody feels, they can connect this one. So week 2 lecture ends here.